Okay, so now let's look at a different example. So h of omega equals 250 j omega plus 1 divided by j omega, and then negative omega squared plus 10 j omega plus 25. So first, remember how in our generic equation, like right there, we had 1 plus the remainder of it, so for quadratic sections. So what we're going to have to do is we're going to have to divide by 1 over 25, essentially. Oh, we're multiplying by 1 over 25 on the inside, and then multiplying by 25 on the outside. So what that turns into is, so you get 10 on the numerator, j omega plus 1, j omega, and then so you get negative 125, 1 divided by 25 omega squared plus 10 divided by 25 omega plus 1. And so remember how j squared equals negative 1? So that's why there's that little negative 1 there. So when we rewrite it completely, you get 10 j omega plus 1 divided by j omega 1 over 25 plus 10 over 25 j omega plus 1. If you think about it, you can rewrite this even further because it's just a perfect square, so it'll be 10 j omega plus 1 divided by j omega 1 plus j omega divided by 0.5 squared. So another way to think about this is the squared, it basically means there's a double pole. Sorry, in this case, yeah, there's a double pole. So you can kind of leave it as it is, but an easier way to do this, just solve it without worrying about too much unnecessary math, is just splitting that apart. So essentially saying erase that, and then 1 plus j omega divided by 0.5. So now you just you draw the Bode plot for this and this on the same graph, so you have a stacking layer. So if you want to do the magnitude, HDB equals 20 log of 10 plus 20 log of j omega plus 1. So remember how there's like a divided by 1 there, minus 20 log j omega and then another minus 20 log of 1. So my software cut off, but let me redo this part again. So 20 log of 10 is essentially 20 times 1, so it's going to be 20. So you'll just have a horizontal line at 20 from that. And then so you have 20 log of j omega divided by 1. So what that means is at 1 it starts increasing. So 20 log of j omega. So it's going to be 0. And then it's going to increase with a 20 dB per decade slope. So that's what that would look like. So for this part right there, what that means is it's basically a linear line starting at 1 with a 20 dB slope per decade, but since there's a negative sign, it's going to be a negative 20. So you have this point right there, that point, and then this part right there means at 0.5, 0.5, that's 5, and then 15. So 0.5, it starts decreasing with a slope of 20 dB per decade. So there's one point right there, there's a point there, and there's a point there. So, but also remember that you have a repeated pole. So this part right there is the same as that purple one. So you'll draw that same thing right there. So when you kind of put everything together, it starts off at 20 and then it just starts decreasing until you reach 0.5, because that's when you have two poles start kicking in. So right there, 20, and then let's just say that's 0.5, 5, 15, right? So you'll be around 10 at that point. So you have 10, and then you have a 40 dB per decade slope because you have two poles. Actually, I lied. You have 60 dB per decade because you have this blue pole, which has 20, and then you have both of these combined, which has 40, so that's a 60. So 60 per 2 decades, so you're traveling half a decade, so that'll be 30 drop. So it would be right around here. And then around at 1, you have one pole kicking in. So, 1, 0. So you have to start increasing, so that means you can just ignore that blue. So you just have a 40 dB slope per decade. So right there, it's not going to be 40, it's actually going to be -60. So what ends up happening is it's going to be -60 right there. So right there, you have a 20 dB per decade, because right over here in this part, there's only one, that blue one is the only one that's affecting it. And then when you get between 0.5 and 1, you have 1, 2, 3. So that's going to be 60 dB per decade. And then right there, you have that green kind of kick in. So that means you have 1 less 20. So that means it's going to be 40. 40 dB per decade. Cool. So now we have to do the phase. So it's going to be inverse tangent of 10 plus inverse tangent of omega divided by 1 minus inverse tangent of omega divided by 0.5 minus inverse tangent of omega divided by 0.5 again, because you have that repeated pole. So you just know that's going to be 0 because that's just a constant. So your actual equation is going to be inverse tangent of omega divided by 1 minus inverse tangent of omega divided by 0.5, and then minus the same thing. So let's draw this phase. Okay. So inverse tangent of j omega divided by 1. So what that means is at 10, it's going to reach 90. So right there, that's going to be a point, that's going to be a point, and then that's just going to be 0. Right there, perfect. And then so for this next part right there, tangent of inverse tangent of j omega divided by 5. So since it's 0.5, let me draw these points. So 0.5, 0.05, and 50, and that's not supposed to be 50, that's supposed to be 5, and that's 50. Okay. So at 5, it's going to be there, 45 at 0.5, and then 0 at 0.05, and then they'll cap out. So that's what that part would look, and then since it's a repeated pole, this part right there is going to be exactly the same as that green part. Okay. So when you draw this out, let me draw some points, 0.05, 0.55. So it's going to be 0 up until when it starts reaching 0.5, and it starts decreasing up until it reaches 0.1. So it starts decreasing and it reaches a value, and then it's going to level out. So not level out, sorry. It's going to still decrease, but not as much. Because this region right there, there's two parts right there. There's two functions that's causing it to decrease. So that'd be 40 dB, sorry, not 40 dB. That'll be 90 degrees per decade. And then this region right there, it's only going to be 45 degrees per decade. And then at some value, it will just level out at 90. And so that would basically be the Bode plot for this function.